Hello everyone, this is Todd Burke and I have another fantastic lab for you. So we will do a little more job training for future astronomers, and this little bit of analytic geometry, astronomy has a big name. It's called the photoelectric photometry of the Pleiades. Well, photometry is just finding the location and distance to an object. You already know where it is. It's just getting how far away it is. And we did that when we looked at asteroids in the fall. So this ought to be a good review. And now we'll be doing it with some stars. We'll be doing it with a star cluster called the Pleiades, or the Seven Sisters, which you all know from the star wall and our sky tests. But also it's up in the sky now. It's a cool thing to look at in the telescope. So it's a good thing to do this time of year. We'll have to review HR diagrams because you guys are going to plot a couple, and we'll get the distance by comparing the apparent magnitude, how bright it looks to our eye, to the absolute magnitude, which is how bright all objects are if we compare them from the same distance. So let's begin. I'm going to find the lab. It's different for you. I'm clicking on programs and CLEA exercises, and there is Pleiades Photometry. And like always, I click on file and log in, and none of this matters. So I just click OK and OK. This is what the window looks like when you begin the lab. We're going to go to run, and it takes a little while here for okay, now it says I have control of the 0.4 meter telescope. Excellent. I'm going to click on dome. This will open the doors so we can see the night sky. We're basically going to operate the telescope just like when we do with star nights at the observatory. And if you look closely at my screen here, you'll see the stars are drifting. And this shouldn't be a big surprise to you if you've been coming to star nights. So the question is, first of all, I'll answer this one. Why is it that the stars are drifting across the field of view? And the answer is because the Earth is spinning. So we're rotating on our axis. If the stars are moving slowly to the right, then what direction is the Earth spinning? Dun dun dun. I could also ask you, what direction are we looking here, north or south? I'll let you answer those questions yourself. To get rid of that problem, I'm clicking on tracking. Now we can point our telescope at a star, and we can take pictures of it or analyze it with a spectrometer. In this case, we're going to just measure the light intensity with the photometer, and we'll calculate the apparent magnitude. We're going to do this with a couple of filters. First of all, let's go to an object. So I'm going to go to set coordinates, and I need to figure out where I'm going. I want to program in here a specific location. So I'm babbling here a little bit, but I've created a spreadsheet for you. Now you guys are going to have to program the spreadsheet, but I've started it, so it has a name. It's got all these columns labeled for you. Here are the things we're going to either find and plug in or have the spreadsheet calculate for us. What I have is a list of 24 stars. These are all different stars in the Pleiades cluster, which is where we're looking. And star number 1 is at this location. So its right ascension means, as I look along the horizon, how far left or right it is. If it's not quite up yet, I can wait. And it's just 15 degrees from rising. It'll be about an hour later, then that will rise over the horizon. So that's right ascension. Declination means how high up I have to tilt my head, or how close it is to the celestial pole. So my first star, number 1, is at right ascension of 3 hours, 41 minutes, 5 seconds. So I'm going to go in here and program. 3 hours is good. I need to change this to 41 minutes. And I need to change this to 5 seconds. 0.5. Dook. Now I'm going to go to declination. Declination is 24 hours. And 05 minutes and 11 seconds. Alright, so I'm going to click OK here. I finished entering my coordinates, yes. And now the telescope is slewing to a specific place. And you can probably not see this in your video of the screencast. But in the center of the square is a tiny, tiny, very dim star, a little white dot. So I'm going to change my view now. It's right in the center of my aperture. This is my photoelectric aperture. So my sensor can take in light from this part of the sky, and it's a pretty small little part of the sky. Although the point of light, that star, is even smaller. So for each of these images, I'm going to have to subtract out any other light that's coming from other sources in the space, so that I know that my sensor is only, my sensor is going to record all that, and I want to make sure that I'm recording in my spreadsheet over here only the photons of light that come from that point source, that star. So first thing I'm going to do is I'm going to boogie over here a little bit. Now that star, I move to the west, and that star is no longer inside the photoelectric aperture. So now I'm going to take a reading. So here's what you do: is you come over here and you click this button. So we changed the view before. Right, here's where I tell the telescope where to move, where to look, right ascension and declination. So we did that. And now I change the view to my instrument, my photometer, and now I've moved away from the star. And I'm going to take a reading without looking at the star. Now if you look here, this window that comes up, this is going to control my data recording. And before I start the count, I want to check this out. There are 3 filters, and I don't need the purple one. This U stands for ultraviolet light. We don't need that. But I want to record both B for blue light and V for all visible light. Okay, so if you look over here, I have a column for B, blue light. That's my apparent magnitude I want to write down. So when I'm done with all this stuff, I'm going to write down the number that's in this part of my window. I'll do the same thing with the, here's the B filter. Then I'll do the same thing with the V filter for this column. And then I'll subtract the 2. So the BV is actually B minus V. And that is the number I really need for my next calculation. So I'm going to record this here. Now I'm just looking at the black sky with no stars in it, and I'm going to click on integrations twice. This means the number of cycles I want to go through. I'm going to take 5. I can change that quite a bit, but I want 5. That means I'm going to take 10 seconds of data, and I'm going to do it 5 times, and then I'm going to average them together. Okay. This will give me my mean sky count. I'm going to start that right now, and it's going to take about a minute. It's going to do 10 seconds 5 times. That's 50 seconds. So I'm going to stop the recording for just a little bit here. Okay, and if you take a look here, now I've completed 5 of these integrations or cycles. And I have a mean sky count of, looking at no star in particular, just the black sky. I got 15.7 photons per second coming in. So I'm going to now do the same thing. I'm going to change filter now to B and start my count. And it's starting off, and I'm going to skip for a few seconds so we don't waste time on the screen. Alright, well, I hit the button a little too early, but we're just finishing up now the 5th cycle here. 8 seconds, 9 seconds, boop, it's all done. So what's interesting to me here is, oh, this is the background of the sky, so we don't have anything there. Now we're done. I'm going to go back to the telescope, move this field of view right to our star. Before I do that, I'm going to save what I've done. So here it's recorded a visible light, basically a dark sky count, and a blue light dark sky count. We didn't do ultraviolet. So this is perfect. This is what you need to have: a V, a number for B, and that's it. And I record it. Okay. So now I can go to return the telescope. So now we have to control the telescope again, and I'm going to move east until I get that faint star right in the center. And now we're going to do the same thing again. So I go to take reading, and I'm going to leave this as it is. 10 seconds and 5 integrations is what I want you to do for the dark sky. you'll play with that a little bit for the stars you're looking at. And the reason is, there's some other things here I want to point out to you. Now, this won't let you take a reading if you don't have the mean sky already figured out. So here I'm doing another count in blue, and I've already figured out with the dark sky how much light roughly comes into my sensor if I'm not even looking at a star. So I want to subtract these, and luckily the computer program will do that for us. So now it is taking a reading off of this star, which is just what we want. But the data will be then record. We'll repeat this process with the next filter, visible light, and then we'll enter it into our spreadsheet. So that's kind of the whole process here. Here comes up the last cycle, 9 seconds, 10 seconds, boom. And now you can see once this data is complete, we also have some numbers here we didn't talk about before. So here's my average photons per second. You're not going to need that. This number is really important. So this is the signal to noise ratio. You want a high number. You want to have a lot of good signal and not a lot of noise or useless data. It's sort of like background static. So we want a high number of static of signal to a low number of noise, and the resulting ratio we want to have be about 100 or more. A lot of stars will get way over 100. You get 1,000 or a few thousand signal to noise ratio, but you want at least 100 so that your error is very small. And with a dim star like this one, this is excellent. You might be willing to, if it's a dim star, accept a signal to noise ratio as low as 70. Okay, so that's what that thing is. We now have our data, our magnitude for the blue light for our first star here. So I'm going to enter it into that part of my spreadsheet. That's 13.335. Alright, so I now want to do the same thing for my visible light. So I'm going to change the filter and do the same thing again. Okay, well, the data has been collected now for our V filter. We completed 5 cycles or 5 integrations, 10 seconds each. Here's the data. They subtract out the mean sky count, which was 15.7. That was when we just looked at the dark sky. And since we have that, it allowed us to take data. Here's all those numbers. Here's the average per second, and now we have a really good signal to noise ratio. It's over 100, so we're good. We're going to take this number. This is our apparent magnitude for all the visible light, and we're going to enter it in the spreadsheet. So the magnitude was 12.516. I'll put that there. 12.516. Good. Now this is the complete process. Let's see here. I'm going to click record my readings. I've got my blue light and my visible light, and I'm going to say OK. And now I'm going to say return to the telescope. Now we have control of the telescope again. Check it out. We could do the second star. I'm not going to right now because you can just hit rewind. But you could hit, want to see this one, go to set coordinates and put in the right ascension declination for star 2. You then could watch the telescope slew over to the new star, whichever the one that is, and you change your view to the sensor here, our instrument, and then you want to first record the dark sky next to the star, and then do that in both filters, B and V, and then you do the recording for the star in both colors, B and V, and then you will have the apparent magnitudes and you'll enter them here. Okay, so you will repeat that process, and you need to fill out the entire spreadsheet. What I'm going to say is, most years I'll have you do about 6 stars, and then you're going to just get the rest of the data from everybody in class. I want you to do this enough so you remember how to do it, but you don't need to spend 3 days in the computer lab just getting data. So we'll divide up this chart. What you do need to do is change this spreadsheet so that it will in fact do some math for you. So I've started it, but you need to program this to do math. This first formula is easy. I want B minus V for this column here. So then you'll record that formula all the way down and every time you enter in an apparent magnitude in B and V columns, you'll have the B minus V already calculated for you. So what I want to do is program in an equation. Here's a little Excel review process. The equations always start with equal sign, and all I need to do is say I want this cell minus, so up here I hit a minus sign, this cell. Now up here it says equals D4, that's column D, row 4, minus column E, row 4, and now I hit return, and it did the math for me. So that's cool, and that's the whole point of using a spreadsheet, is it makes your life easier. Now if I grab, you see the bottom right corner here is a dot. I'm going to grab that thing with my cursor, I'm going to click it and hold it and drag it down, and it's going to repeat that formula for me all the way down. My window didn't allow me to get to the final row, which is star 24, so I'm going to grab star 23, I'm going to grab that bottom right corner, I'm going to hold it, click and drag. Boop. Alright, so now if I were to put a number in here, it's going to naturally do some math for me. If I have the number 10, and I subtract the number 3, automatically it says this column minus this column, and here's the answer. Obviously those are bogus numbers, I'm taking them out. Okay, so your life's pretty easy. You need to do about 6 stars, write down the apparent magnitudes for the blue filter, and then apparent magnitudes for all visible light, and then record the data from your friends as well, so your whole spreadsheet is complete. Now we have some more math over here. First of all, this is a column you're going to just get off of this table here. Let me see if I can open this up. So I have this table, which is part of the printout I put into your student account on the network, as well as printed and handed you. So this is going to tell you if your B minus V is 0.89, so let's say 0.89 is right there, then your absolute magnitude is 5.9, and you have that information also. Alright, well some of you are wondering at this point, well what do we do if it doesn't work out so perfectly? What happens if our apparent magnitude isn't listed on your chart and it's in between two of the rows on the chart there? We got to figure out, well, what exact number should we write down for the absolute magnitude? Well, smart, nice going, by the way, thinking of that question. You get a gold star. Well, you're going to make your own HR diagram. We've played with them before, and we'll talk about them again, but you're going to use the data from these 24 stars and do a little graphing part of this lab on your own by hand on graph paper. You're going to use your own work to answer this question. Nice! So, the answer will lie in your graph there. Basically, I'll tell you quickly. If you look here, here's a generic HR diagram. Luminosity is apparent magnitude. That's how bright a star looks to your eye. So you will have graphed 24 stars, and you'll end up with sort of a main sequence and scattered stars. And you're then also going to label the y-axis with absolute magnitude. So you'll be able to take a star, make sure you lined it up just right, and then come over to the other axis here, and the other label for the y-axis, and say, oh, the absolute magnitude must be, well, whatever you labeled it as. So stay tuned for that. When you get into some details that you're not quite sure about, you'll find that you already have calculated the answer, and it's easy for you to move forward. Nice job. Last thing, and the main point of this lab is to get the distance here. Now, we think this type of open cluster is made from a bunch of stars that formed at about the same time from the same interstellar cloud of gas that collapsed. And so the nebula that gave birth to star number 1 also gave birth to star number 2, which also gave birth to star number 3. So our distances are really similar. They're all in the same part of space, and they're all about the same age. So we're going to have the assumption that they're all about the same distance. That means that they're apparent magnitude, and for that apparent magnitude we're going to use this column, the V column, all visible light, as we collected in our photometer. We'll say that's their apparent magnitude. We'll say that they're all about the same because they're all about the same distance. Now, there's a formula to calculate distance. In fact, that formula is right here, this big thing. And this formula, which is a logarithmic formula, is basically a huge exponent right here, is what I want to have the computer do for me for every one of these 24 stars. And I want that to be here in column H for distance in parsecs. So I'm going to click on this first cell that's for star 1. It's in row 4. And up here at the top, I'm going to type in a formula. So I need to start with the equal sign. Now it's going to be hard for you to see what I'm typing very small here. And I found that I can zoom this spreadsheet, but it doesn't zoom the this box up the top, this window doesn't get any bigger. So it's not going to be easy for you to see. But I'll read out loud what I'm typing, and it's basically this formula. I'm going to start right here and type that. Now I can't do subscript, so I can't say, hey, this is an exponent. These numbers are really small and they're typed up higher. This part here I can't do. So what I will do is I'll hit Shift 6, the number 6, and I get that caret sign. And that caret sign means, hey, this is an exponent. Alright, so up here I say equals, and I want 10, and then I want the caret sign. So Shift 6. The caret looks like an A without the little center bar, or like a little mountain shape. So I have now an exponent, and I'm going to put in 2 parentheses, 2 opening parentheses, equals 10, shift, there we go, 2 parentheses, and I'm going to say I want my apparent magnitude, small m, and that is going to be this column here with the column E, the amount of light that we captured with the V filter. So I'm going to click on this cell, and then I'm going to say minus my absolute magnitude, this cell, and then I'm going to say plus 5. Kind of weird. I'm going to end my first set of parentheses, and I'm going to say divided by, so that's a right slash by 5. And I'm going to end my second parentheses. So this whole thing says 10 caret double parentheses E4 minus G4 plus 5 end parentheses slash 5 end parentheses. And now I hit return. I have a distance there, 210 parsecs. Almost done. So I've programmed one formula here, B minus V, and that was easy. One formula here, and that was hard. We just did that. And now I'm going to convert this. I want this distance. A parsec is 3.26 light years. Well, we use that in astronomy quite a bit, but not in my class so much. So that it's a number that makes a little more sense to us. Let's just talk about it in terms of light years. So I'm going to take this number, multiply it by 3.26 to see how many light years that is. So I am going to make my last formula. I start with an equal sign. I'm going to say this cell, so I just click on it, and it says H4. Perfect. I'm going to say asterisk, so Shift 8 gives me an asterisk, and that means multiply times 3.26. And I hit return. This tells me that that's a distance of about 686 light years. Alright, well, you now know everything you need to do to complete this spreadsheet. You'll need to go back to, there we go, go back to the lab and to the telescope and finish getting data in the photometry of the B filter and the V filter for your stars, and then record your the same numbers from everybody else's star, and then put them into your spreadsheet here. For each one, you'll want to look up the apparent magnitude, which is from the chart that I gave you, and then you ought to automatically get your distances calculated for you, both in parsecs here and in light years in your column I. And then you have 5 questions to answer on the worksheet that lists it, that gave you this chart. There, that chart. So, the final part of your lab will be to answer these questions. Number 5 is a bonus, but I recommend you guys do it. I hope you guys enjoy the lab, and certainly I hope that this set of directions is clear. That's it. Make me proud.